Johannes, who is an undergraduate here. He's a physics or a math major. It's hard to tell the difference at this point. I've been working with him, and we've been looking at spin chains from first fundamental point of view for about 2 years. We're working on his senior thesis, which is trying to recreate the state-of-the-art numeric methods for computing observables like ground state energy and some evolutions of 1D spin chains. And we're trying to do a coupling of or a system of 1D spin chains and see how they interact using this method and try to test this this numerical method that exists in the literature. So he's going to give us an introduction to some of the key concepts of DMRG. Yeah, it just points, it doesn't click really. Okay, well, it doesn't click, period.
Sure. Okay. All right. So yeah, it's excellent. I'm very pleased, to be here. I'm really excited to give this talk. The only unfortunate thing is that I don't have a lot of time, so I can only give a very brief overview of the ideas of DMRG. As Axel said, we're motivated by quantum spin chains. So things like the Heisenberg chain or the Heisenberg-Ising spin 1/2 chain for modeling magnon dynamics and certain materials such as CRISPR. So I really want to talk about 3 things. The first thing is I want to motivate what we're talking about. I want to motivate that quantum mechanics seems to have a problem where it's elusively complex. And then following this, I want to talk about matrix product states, which is the language that modern DMRG algorithms are framed in. And then finally, I'll give a heuristic introduction to DMRG, and then talk a little more about the details with DMRG and matrix product states. So the dimension of the associated Hilbert space for some quantum system grows exponentially with the degrees of freedom of the system. For a quantum spin chain, it grows something like 2 to the L, where L is the length of the spin chain. So if we have some many-body quantum wave function, so either L particle occupancies or L spins, it's exponentially complex to represent the wave function. It's very difficult. There's a famous, albeit misleading, quote by Walter Cohen in his Nobel lecture that in general, the many electron wave function psi for a system of n electrons is not a legitimate scientific concept for large n. But this quote is misleading because we work with quantum systems with large n all the time. I mean, we're doing condensed matter physics here. I mean, the systems have very large n. So then what's the problem? Well, for quantum systems, oftentimes, most relevant in our case, the relevant physical information of the quantum system doesn't span the entire Hilbert space. And so more precisely, in ordinary quantum mechanics formalism, we don't distinguish between physical or non-physical states. So physical meaning physically relevant, non-physical, just information or things like this. So how can we understand these quantum systems? How do we get rid of the non-physical states and focus on what we want to understand about the system? Well, tensor networks provide a very natural language to pick out these physical states, which are referred to in the literature as low entanglement states of the system. Low entanglement because they only interact locally. If something was non-local, we'd have a lot of problems in physics. Matrix product states in particular is just a particular tensor network that captures 1D entanglement for gapped systems. So it's very important that it's gapped actually. And so certain quantum spin chains aren't gapped in certain regimes, I suppose, like the Heisenberg-Ising XXZ spin chain is not gapped for delta -1 to 1. But most systems are gapped. And so gapped in this case means that between the ground state energy of the Hamiltonian and the first excited state, there's a finite gap here. There's not a continuous spectrum of energy. So in general, we can take a wave function psi and we can represent it in terms of its wave function amplitude and the states, the cats. Okay? And in this case, this sum over n is just sum over all configurations of the system. So again, the C with the subscripts n, n1, n2, so forth, is the wave function amplitude. Okay. Matrix product state representation of this wave function would be that we take this C, this wave function amplitude, and we represent it as a product of tensors or matrices. So again, these CNs, these are really scalars, and then these A matrices are tensors. So constructing these matrix product states, we really want to use SVD, singular value decomposition. For those that aren't familiar, you can take some vector or some matrix, and you can decompose it into a product of two rotation matrices, that's U and V, and then a diagonal matrix of singular values, that's S. So before I get into some of the theory with these matrix product states, let's go through a very quick example. I just want to illustrate the idea of these matrix product states for wave functions. So suppose we're given some wave function. This is just a superposition of these states. What we want is we want to represent it as this matrix product state, this sum over all configurations of the system of these tensors with their respective cats. So looking at the wave function psi, we can construct a matrix that has ones in all of its entries. So the coefficient of this up state is 1, and then so forth, so up, down, down, and then up, down. These all have coefficient 1. So we can construct this matrix. And then following the idea of matrix product states, we want to do a singular value decomposition. So if we do this, we end up getting, this is our U, and then this is our SV dagger here. And then the way that we get these A's is, for this example, just by inspection. So this AN1, this first tensor, has the up component is this row vector 1 over root 2 minus 1 over root 2. So that's this row of the U vector. And then the down component is just the second row of this U matrix. And then always the case with matrix product states, the last matrix in the product is the columns of this matrix in the SVD, the singular value decomposition. And so this is just a very quick example to illustrate the idea and to motivate the theory of matrix product states. So again, more generally, we want to take this wave function amplitude and we want to represent it as a product of these matrices or these tensors A, superscript, and then whatever the state is. These wave function amplitudes are exceedingly complex for large systems. This is the problem with these kind of quantum systems, is that the tensor of coefficients, the wave function amplitude, grows exponentially with the size of the system. And so in our case, we begin constructing, because our goal is to get to this matrix product state, we begin by reshaping this tensor into a matrix psi with dimension d by d L minus 1. And L is just the size of our system. So if you think of spin chains, it's just the length of the spin chain. The coefficients are related in the obvious way. The SVD of psi gives this. So I do want to highlight that this single d is captured in the N1, and then all of the dl minus 1 terms are here. So this is why the notation is, we're just saying what the dimension of psi is here. We're making it obvious. So if we do this singular value decomposition, we get the usual U, we get the S, we get the V, but now we have this suspicious sum over this A1 all the way up to R1. So with matrix product states, this sum is extremely important for the DMRG algorithm later. This sum is over a virtual index, which is called the bond index or the bond dimension of the matrix product state. This R1 is it's less than or equal to the rank of this psi up here. So in this case, R1 is less than or equal to D. As we see later with the DMRG algorithm, what we seek to do is to truncate the SVD, namely truncate this S matrix, such that we can reduce the number of sums that we have to do. We can reduce this upper bound R1. Because then this makes, this makes the algorithm much faster, more simple to calculate things. And so this SVD, what we can do is we can combine this S and this V dagger into these coefficients. And so you'll notice this bond dimension A1 has been shifted into the index of these this wave function amplitude. So before it was Cn1, N2, so forth, but now we're summing over the bond index. Okay. And this theme will repeat as we continue. So again, you can be decomposed into D row vectors. That's what we did in the example. We just looked at the row vectors of the first matrix in the SVD, and then we determined by inspection. Here, U is the D row vectors A super N1 with entries given by A super N1, and then this bond index down here. And I can say more about this later, but I'm trying to motivate us. So we can continue this process. We can just keep going. So we have this, but we're not quite at the matrix product state representation yet. We only have one of these A tensors, and then we still have this wave function amplitude. So we just continue. Let's reshape this tensor of coefficients into a matrix. Notice the notation here. The bond index has been picked up on this psi with dimension R1 D by dl minus 2. And so just to make sure we're on the same page, this wave function amplitude so far has been deconstructed as following. We're not at the matrix product state representation, but we're getting there. And so now what we do is we take SVD of this psi term as many times as it takes. And so in this case, I'll stop it a second time. I don't need to put us to sleep going up to n. But we have this first sum, A1, which is over the bond index, but now we're introducing another bond index. And so every time you do SVD, you introduce another sum that over this bond index. And so to answer, maybe a question that we might have, well, why does the bond index matter? The bond index is quantifying the entanglement of the states in the system. So in this case, because contextually we're dealing with a spin chain with open boundary conditions, not periodic. But here, so this first term just depends on the first site of the spin chain. This term is the interaction with the first site and the second site. So this bond index is giving the interaction between the terms, the entanglement, or not the terms, giving the interaction between the sites of the spin chain, or the entanglement between every site on the spin chain. And so when we get to the DMRG algorithm later, this is a parameter that you set in the algorithm. If you have a very large bond index, then you can capture more relevant dynamics of the system. If you have a very low bond index, then you can only capture very simple dynamics, nearest neighbor, things like this. Okay, I just want to remark, I won't really go into detail with this, but operators can also be deconstructed in an exactly analogous way to matrix product states. And so I just kind of outline this state. These are analogous to the A super N1 tensors, but now they have this extra index, which is N prime 1, just because it's an operator. So let's begin with DMRG and matrix product states. And I did want to start this with a heuristic overview. I want to give motivation because we can very easily get lost in these matrix product states. And so we want to talk about what DMRG is doing. Given a spin chain with these sites, each of these sites, we can immediately construct, it's not in an obvious way, but it's not super difficult either. We can construct the system into two blocks and then two sites in between the blocks. And these blocks have some Hamiltonian. We can say this is the S Hamiltonian and the E Hamiltonian. And then there's some kind of Hamiltonian going on in between these two. Point being is that DMRG will absorb sites into the block with DMRG truncations. I won't say what that is immediately, but this is, I will actually, I lied. DMRG truncations is just truncating the singular values in the singular value decomposition. So the blocks get larger with more sites, but the dimension gets smaller. The dimension of psi gets smaller because we're getting rid of singular values. And so we're decreasing the rank of psi. And so this makes the algorithm very nice, very fast. And so DMRG, because it's based on the variational method, it's a sweeping algorithm. So I guess in this case, this is some paper, I don't have it cited here, but it's at the end. In this case, we go from right to left, and then we shrink this down to its minimum size, so only one site or something like this. And then we start again. We sweep over the right side, and then you kind of repeat this however many times you want to get the desired accuracy. And on every sweep, you're truncating more and more singular values. So you're reducing the dimension of the Hilbert space more and more. So DMRG it's based on the variational method. So its goal is to find the ground state energy. So what DMRG really does is we find some matrix product state of this wave function such that the energy is minimized. So the expectation value of this is Hamiltonian, whatever it is, XXZ, Heisenberg Hamiltonian, doesn't matter. So again, I want to recall that this Hamiltonian we could represent is a matrix product operator, just following a very analogous procedure for matrix product states. And again, I also want to recall that what we do with matrix product states is we take this wave function amplitude, we reshape it to this this tensor, this d by dl minus 1, and then we can do SVD of this psi, and we get these singular values, the singular value matrix right here. What's important with DMRG, and kind of as I said earlier, is that every time you do this, so every time we decrease the rank of this psi, or just sum over more bond indices, we can truncate the singular values of the system. And so the number of singular values determines the rank of psi. And so if we get rid of more singular values, we'll truncate psi more and more, and hence we'll truncate the Hilbert space. And this makes it very easy to compute things. So this psi is a matrix product state. So we have this product of matrices, and truncating this S reduces the dimension of the Hilbert space. So remember, this Hilbert space grows exponentially. And so what we're doing is we allow it to grow exponentially, and then we say, okay, we truncate. And then we let it grow again, and then we truncate. And then we let it grow again, and we truncate. And we repeat this process until we're done, until we reach a desired accuracy. And this last bullet point is that we optimize locally. So if I go back to this slide, optimizing locally means that we have some interaction between this site and the block. So it's getting absorbed into the block. And so this is why the block is growing. And then eventually the left block will reach only one site. So you can't get rid of any more. And so then you restart and you start absorbing these sites. And this is an analogous procedure to doing this SVD and absorbing these this singular value matrix and this V together. Okay. So this is what it means to optimize locally. It makes sense that we have some local interaction between these sites and the block, and they get absorbed, and then you continue until there's no more left to absorb. Okay, so this was the overview. Thank you for listening. Of course, this slide 12 reference, this is the heuristic overview that I showed. And of course, any questions?
Questions?
So what is the outcome of the calculation?
You get ground state energy.
Okay.
Yeah.
So ground state energy, and then you compare it to what to validate your simulation?
Ah, I see.
Yeah, that's a good question.
Yeah.
Must be some sanity check somewhere, right?
Yeah, well, okay, one way that you can do this, so the DMRG is for strongly correlated 1D quantum systems. This is what's most commonly used. DFT is another way that you can find these ground state energies, but DFT avoids the many body wave function entirely. DFT use the electron density to figure out the ground state energies. With DMRG, you say, we don't need to do this. The system is sufficiently simple such that we can still work with the many body wave function, and we can just get rid of the non-physical states. So things that don't matter for the dynamics of the system.
You can also compare it to, you can do the psi h psi and square that and compare it to psi h square psi. See that it's that's actually converging. So you can look at other quantities that converge as you're sweeping through different states.
How do you ensure that you are in the global minimum, not the local minimum?
Yeah. So with DMRG, this is a really big problem. It's stuck in local minima.
Yeah.
Because if your bond index isn't sufficiently large, then it's the system can't get enough to jump to the global minimum or something like this.
That's why it's important to have some sanity checks, right?
Yeah, so yeah, those are good questions though. Yeah, we should.
So I'm not sure if I quite understood it, but I'm familiar with SVDs and how you can do a low-rank approximation by taking out the smallest singular values.
Yeah.
So that's basically what's going on here, right? And then I guess the second part of the question is, what does the sweeping from left to right, like expanding the blocks, which I assume are the systems you're considering, what does that do? Can you explain that one more time?
Yeah, this is a good question. The reason that you expand the blocks is because what you start with is you have some spin chain and you've segmented it. You have one Hilbert space or one Hamiltonian that describes the dynamics here, one Hamiltonian that describes the dynamics here. And now what you want to do is you want to, and then you leave out these two sites in the spin chain, something like this. And now every iteration of DMRG, you seek to absorb this spin site. And so this is very similar. We can see this in the MPS calculations. Yes. So this state is all of these sites on the spin chain. Okay. When we do SVD and we create these A matrices, this is like getting absorbed into the block. This is what it means. Okay. And these bond indices, again, this is just capturing the entanglement between every site of the system. Does that answer your question, or maybe not so much?
Maybe I can add a little bit to it. So can you go to the last slide? So the last slide in the presentation.
Oh, okay.
Yeah, this one. So here you have this psi state that it's A and 1 through A and L, and you're trying to minimize the E quantity. So essentially what you're doing is you're trying to do steepest descent, try to like minimize it through steepest descent. But what this representation of psi gives you is that you can try to, instead of trying to like move in the dimension space of C, the coefficients, you can move in the dimension space of each A individually. So you move locally in one of these coefficients. And so you try to minimize in that space, and then you minimize as much as you can, and then you move to the next one to try to minimize there. And then you keep moving from A's to try to minimize in each one of them. And by moving a little bit in each one of those spaces, you eventually try to like converge to a minimum.
And you consider each A matrix independently?
Yeah, and there's some technicalities that you need to break them up in a particular way, like doing SVD, so that you're only minimizing, like you actually capture the local spins properly, and the interaction of the local spins. So it's bookkeeping.
Question there?
Yeah, so I guess I'm generally familiar with the RG as like a you know quantum field theory, like as a field theory construct. Would you be able to point me to like where your I guess fields are in here, if they like sort of at what layer you're doing a field theory here, or is that am I thinking about it totally wrong?
So I was very afraid of this question. I don't know renormalization group theory, so I'm very unfamiliar. I'm exactly unfamiliar with what you just asked. So to be honest, I don't think that I can point you to that. I'm not sure at all. Sorry.
No, thanks.
It's a discrete field, but I guess the field here is the spin. At each side, there's like a spin vector, S, X, S, Y, S, C, and those are the quantum fields. Yeah, so each lattice site has these operators associated to it, and that's the discrete field. So the field variable is the lattice site.
So you said that the outcome of this is computing things about the ground state.
Ground state energy.
Ground state energy. Is there a way to add a little bit and learn about excited states?
Yes, there is. Depends on what you want to add, but sometimes it can be easy and sometimes it can be very difficult. Of course, because it's only for gap systems. It's once you get to the first excited state, it's a little harder to go further and further, right? Because you can't. It's hard enough to reach for the first one. Going any further is really difficult. But things like just off the top of my head, like the spin structure factor or something like this, you can find.
There's also DMRG, which is time evolution. So you can also like start from a state and evolve the system according to the Hamiltonian. So, but yeah, it seems like the key is all this like bookkeeping of matrix product states and like doing SVD. And I think that's data science, right? SVD.
I'm a data scientist. That's what I do.
So isn't the ground state, like, don't we already know what it is? It's like all spins aligned or anti-aligned, so like in CRISPR or like, so why can't we just put it in? I mean, the Hamiltonian will just give it to us, right? So it will just be obvious visually what the ground state is, right? So then this be kind of overkill.
Yes, I think
It's not just for spin systems, though. It's for any strongly correlated 1D quantum system. So like, in that case,
But we're writing a spin Hamiltonian, well, at least, right? So we are describing, like, isn't that the system we're describing? It's not just spin.
yes. So the ground state, yeah, I think you can just guess it. You're right. But I think as Johan was saying, you can also compute other things. So like the spin-spin correlation, you can like beef it up and do other things, and you can do time evolution too.
yeah, also DMRG has precedented use in quasi two-dimensional systems. And so when you increase the complexity of the system, I personally don't know if you can keep just guessing the ground state energy and be correct every time. So like, for instance,
For complicated systems, you can't. Yeah.
well, exactly.
Any
Which
of
is why it's
yeah. Yeah. Oh, yeah, yeah. Well, I just mean, I'm trying to tie it back to CRISPR.
Right.
So.
Any other questions?
I'm so sorry. This is another, I think kind of annoying question. But do you have a sense of like when, like your numerics just kind of explode as your renormalization time goes to, like as like you know, like for the ordinary renormalization group, you get you get numerical instability if you try to like do it on like a turbulent system or a system with turbulence. And I guess my question is, do you have do you know if there are relevant things that make this algorithm get mad, I guess?
Johan?
So sorry.
Short answer, no. We're still in the stages of like running it for like simple systems. So we're focused more on like theory and basic examples at this point.
Okay, cool. Sorry.
No, it's a good point in case we see this, we know to talk to you.
I would say that kind of on that, yeah, exactly. We're still in the early stages, but at least in the literature, it doesn't seem like there's any places in which you would blow up. But as I mentioned to Oksana, there are situations that it will converge to something that's not like a global minimum. So you'll get stuck very frequently in local minimum. And so this happened when I was running some calculations, but yeah, that's the only case that we found so far in which the DMRG can get stuck.
Any more questions? I think we'll call it for now and thank the speaker. All right, we'll take a 5-minute break, resume at 5:20.